Okay, very good. Thank you all for being here. I think it's a huge pleasure to have Dimitris actually talking to us. I think we're academic cousins, right?
We're related in some way. I'm not sure what the way is, but yeah, there is a connection.
Right. As you have seen, he has if you have seen his bio, he has like so many awards that if I want to cite them, then half the talk is going to be about all the awards he has won. I'm going to spur him from that, and I think it is much more important to hear what he has to say. Just one note is, I think Dimitris is one of those rare people who have an amazing taste in problems and super creativity in solving them. That is what I have witnessed over many, many years. And he has shown it in so many different ways, in so many different fields. And today he's going to talk about some of these vignettes with us that I'm super excited about.
Thank you so much. I mean, this is very generous. And it is true that I guess we date back from the years of information theory that is sort of like a long forgotten area now.
Forgotten field.
Forgotten field. Yeah, so basically just a quick note. I'm a professor at the University of Wisconsin. I'm also a research manager at Microsoft Research. This is a very atypical talk for me because I will talk a lot more about sort of the meta process of doing research and kind of the way that I've experienced the arrival of agents, and the way that I feel about research now is that it really is the golden age of asking questions. And I want to try to convince you about what I mean, with this statement. By the way, please interrupt me at any point if you have questions or you want to discuss any aspects of the stuff that we'll talk about. And so over the past few months, since February, the way that I personally do research has fundamentally changed. I think this is true for many people. And I want to walk you through a few projects, 3 in particular, that I ran since February, talk about what I learned from each one of them, and then share a few thoughts and questions at the end that I don't have really good answers for. And this is a bit of a weird talk again. So this is not going to be about a particular, big research thread. It's mostly 3 different vignettes that I was very interested in, and I was able to answer all by myself with the use of agents. And they had some small impact, at least in the way that I perceive things. So before I get into the projects I will talk about, I want to set up a little bit something that I think maybe a lot of us have experienced at some point, which is basically that most ideas that we have, they kind of die quietly. So you never really pursue them. And that's not because they're not cool or you don't like them, but it's mostly because it may be hard to justify working on them, right? So you may be busy with a gazillion other things, but you have this idea that, you want to scratch in the back of your head. And these perhaps are ideas that are, speculative, and you can't justify spending time on them, or maybe the payoff is unclear, or maybe there's too much engineering for too little expected reward, which in my case, I'm also old and I can't code anymore before agents. So it's one of those things where, maybe you tell a colleague and then, you both agree it's really cool, but nobody really works on it, right? So I've had several of those ideas that have accumulated with the years. And I've been carrying them with me. And after the arrival of agents, 3 of them are now fully answered. And I'll show you all 3 of those ideas I had in my mind. And so this kind of like started in February. I was doom scrolling Twitter and I see this particular post, which was about someone that did a lot of fine tuning on a 7 billion parameter model and was able to get really high accuracy on GSM-8K. So GSM-8K, if you don't know, it's kind of like a high school math type of standard kind of like benchmark. And he said that he did this with only 13 parameters. So he kept, it was a Quen model, it was only fine-tuned on its LoRa adapters, only 13 parameters. And I was very curious about it. So he basically said, I only changed 13 parameters in the model, and the model magically becomes, gets, I don't know, 90% on GSM-8K. And so I'm sort of sitting there and thinking about this. I feel very surprised. And I think to myself that this cannot be the model. It can't be just a model sort of like, being that good so suddenly at GSM-8K. And it has to be about the data as well. It has to be about the evaluation questions. And I don't know if you've ever seen a GSM-8K problem before, but they're very sort of like in your face algorithmic. Like Mary has 16 eggs. She eats 3 of them, bakes another 4, sells a bunch of others. How many eggs does she have by the end of the day? So it's kind of like from the question, it's kind of like really clear the function you have to evaluate to answer, how many eggs does Maria have at the end of the day? And you don't really, it felt to me that maybe you don't really need a language model at all for that. So maybe all you need is a parser and a calculator, like a really good parser that can extract sort of the numbers of the question and the sort of like the relations and the operations and whatnot. And perhaps this could, in some ways, if you stitch code together in some way that I had no idea, you could have a solver for GSM-8K that is not a language model. Okay, so this is, it's sort of like a silly question, all right? Because people have been trying to master GSM-8K for years with language models. Now it's fully saturated, by the way. It's not an interesting data set anymore. But in any case, I was there sort of like sitting, could you solve this with a ton of code, like a symbolic method, with a ton of if then else that extracts, numbers and operations from the question and tries to answer in some way, okay? And so in the old world, like before February 2026, I would kind of like ignore this question. It would just like sit at the back of my head for years, and then it would slowly wither and die away. Because this is sort of like the type of thing that's not a paper. I don't want to waste my students' time or a semester on this. And it would, for me, it would take, I don't know, several weeks before I even have a working kind of like solution. And so this overall type matches quite well to the sort of ideas that I would never really scratch. It would just stay there, bother me, I would never touch it. But it was a Sunday and I wasn't doing anything. And so I effectively wrote a very long prompt to both Claude Code and Codex, the 2 most popular agents, I would say. And I described the idea that I had. I listed some high-level directions. And then I asked the agents to basically just iterate autonomously. Do not ask me any questions. Just come back with a solution. Okay, so that was like roughly the shape, if you will, of my process. And then I just went on my day. It was a Sunday, did other things apart from, doom scrolling and talking to Claude. And I came back to my computer. So, by my computer, I mean, Claude Code and Codex were just like running stuff in the background. I left them alone. I went to bed, perhaps. I went back to the computer several hours later. And both of them came up with some kind of a solution that achieves, roughly speaking, 15% accuracy on GSM-8K. All right. This is far above random guessing, but it's not very impressive, right? This is not what I was hoping for. And this was definitely not a paper. And honestly, it's kind of lame. Okay, so this is not super cool. But this silly project mattered to me quite a lot because for the first time, agents effectively proved to me that they could do exactly what a very good student would do in their first week of running a project. They tried things, they iterated, they wrote up what they thought would work, what didn't work, what failed, what was the final solution. And they came back with a number, right? So they're like, I could achieve this accuracy in GSM-8K with no training weight. So this was not a model that was trained from scratch. It was just like stitching code together effectively. And the point is, like, I had done none of this work, right? The only thing I did is I sort of like guided the agents to try a silly idea I had on a particular problem. So that allowed me to scratch this itch. And so I want to slow down for a second here because what has just happened to me on that Sunday is exactly the kind of process I keep coming back with, any type of agent projects that I have, which is basically I have an idea that I want to scratch. It's not a publishable idea, but it's an idea that bothers me. I really want to have some kind of an answer. And I give a high-level direction to the models, which is not pseudocode. There's no, it's sort of like a research plan, like a very similar thing that I would say to my students, a description of the question and a few avenues that I would personally sort of like try to attempt. And then the agents do all of the work, right? So not most of it, literally all of the technical work happens on the agent side. And by that, what I mean is like, they will set up the experiment, they will create data pipelines, in this case, symbolic parsers. They will run a bunch of iterations over, the setup. They will track the failures and write up what they find. And I look at the numbers. So my role is this: I look at the numbers, I figure out if they messed up, if they did something weird, and then I tell them what else to steer towards, right? And then I just wait. And if you've ever worked with a student, this feels very familiar. It's kind of like, you give a direction, they go away for a week, they come back with a number, and then you tell them that number is wrong, work one more week, right? So this is very, very classic, and to some degree is an approximation of how you would work with a junior researcher. So that was really mind-blowing for me. So this was, again, in February, it was the first time I was using Claude Code and Codex, and I was extremely surprised at how close this mimicked how I work with students. And so, it really dawned on me that basically something in the way that I work has like completely changed and shifted. And for a couple of days, I actually experienced major intellectual dread. I somehow felt like, we're going to be totally automated, like we're going to go away, right? So this was kind of crazy because most of the technical work that I've been used to, and the technical work that I've used, to train students with, seemed like it has come very, very close, if not completely, it has come very close to be automated. And then I wondered what is left. So what do we do in this new world? And so eventually I stopped panicking about AGI taking over my job, and I started thinking. And the way that I would describe what had basically transpired that Sunday morning in one sentence, that basically I felt that the distance between a question and experiment had completely collapsed, which, if you think about it, is completely incredible. Like, what a great time to now do research where all the hard stuff that, would be very frustrating because you will have to work weeks on it is not completely, lifted from your shoulders. Like something else is doing it for you. And that is incredible. That's really incredible. So everything I'm going to show you now is evidence for this. I'm going to call this, this is the theorem I'm going to prove in this talk, right? So this is what I've experienced, and this is what I think has happened to many people working in this area. Like this is what many people experience working with agents in this area. So before I talk about the particular projects, and they're all a little bit simple, hopefully we'll get a chance to talk a little bit more about them. But I want to spend just 1 minute on the actual process, because people sort of like ask me, what is exactly the thing that you're doing, and it's dead simple. It's very, very boring in some ways. Like there's nothing magic about it. So here's what happens. So basically, I have an idea, like whatever can you build a symbolic model or I don't know, solver for GSM-8K? Have a bunch of those weird ideas. It shows up, it's stored somewhere in my head, and then I want to scratch it. So what I do is I go on a long walk. All right, so I go on a couple hour walk. During that walk, what I do is I record a very long voice memo. Right, so like I literally talk to my phone. And sometimes when when I'm on a walk and people walk around me, I put it on my head so that people think I'm talking to somebody, right? Because it's kind of weird. Talk on your phone. So I talk on my phone for a long time, describing how I would describe to a student or a collaborator my hypothesis, the research, the idea, the experiments I have in mind, what I think could work, what I think is a dead end, like literally my whole mental framework for a particular problem I'm interested in. Then I take this voice memo, I transcribe it into text, I paste this brain dump on Claude or GPT, whatever you're using, and then I ask for a prompt for the agent. I'm like, I want to solve a problem. Here's a voice memo of me describing it. Create a prompt for Claude Code or Codex, whatever you're using, to effectively autonomously run the experiment that would answer this question, given the sort of like, the ideas and whatnot I've described in the voice memo. And then, Claude takes, I don't know, a minute to create a prompt for the agent. I copy that prompt to now the agent, hit enter, and then just wait. Okay. So what do I do? Like I wait, and then at some point, it may be a minute, it may be an hour, it may be I don't know what, the model comes back or the agent comes back with results. And then I look at the results, and there's many variants of what can happen. Maybe the agent messed up, and I'm like, this definitely does not make sense. You're I don't know, you're training on the test set. You shouldn't do this. Like there's sort of like, that's the part where I think being a strong verifier matters a lot. But the high level idea is like you look at the results and then you steer towards whatever direction you think makes sense. and then the model does something else, and you kind of like wait and sort of repeat this process. And what I just described, I think, is basically the scientific method. You state a hypothesis, you design experiments, you run them, you look at the results, and you iterate, and you kind of like update sort of like, this process. And that's all there is to it. And the only thing that changes now versus scientific method a year ago is who does the technical work, right? So that's basically, in my eyes, what has changed. And that's it. It's not more sophisticated than that. That's literally every single time I post like, a paper or an article or a blog post or whatever about the problem, this is exactly the method I follow, right? And in many cases, when I'm like, there's a part after this, which is me basically writing my findings or Claude's findings. And in many cases, that takes more time than actually, the scientific work. But the whole point is that this is basically what it is. Okay, I just go for a walk, I record an idea, I paste it to Claude. Claude Code runs the experiment, and we kind of like iterate. So that's the process. And what I'm going to talk about follows this process, like the 3 vignettes I will talk about. So 3 projects. So the first one is, I call it addition under pressure. It's basically autonomously, having the agents autonomously try to train the smallest possible transformer that can add 10-digit numbers. The second one is figuring out how correlated evaluations in coding and math and whatnot are, and how much can we predict the scores of a new model without running evaluations. And the last question I had for a long time is whether you can train a transformer to act as a full-blown computer where you can run an operating system on. Okay, so these are 3 questions I sort of like, carried with me that I scratched, and I will show you sort of like the results, if you will. And you will notice that they have nothing in common. And that is intentional, because sort of like, I was, what I want to convey is that, these are not connected. It's not like a research project. It's like now I can kind of like, I'll talk a little bit about this idea of like doing high temperature research. Like I have all these ideas, a breadth of like random stuff that I think is kind of cool, but now I can actually dive deep into each individual of them, because someone else is doing the technical work and I'm not wasting human hours for it. And this is really cool. So with just this very short summary, I'm going to dive in the first one. But before I do that, I'll just take a 5-second pause just to see if we have any introductory questions, or if we're all on the same page on kind of like, what we're going to talk about. All right. So, okay. Addition under pressure. Before I tell you what I asked the agents to do, I want to give you a little bit of context. Because for me, this was not a random question. I've been actually working on this problem of addition and arithmetic for transformers for quite some time. All right, let's see. So, okay, so this is me basically, this little bunny, and that rabbit hole is basically arithmetic. And I've been basically obsessed with arithmetic and transformers for a few years now. And long enough that my students have given up trying to talk me out of stop working on it. But there's sort of this very simple question that fascinates me quite a lot, and I'll show it to you in its plainest form, right? The question is this: I have a language model, but it's not trained yet. It's like a tiny transformer. It's a baby transformer, a very small one, something that you could run on your laptop. And I wanted to teach it only one thing. It doesn't know how to read and write and speak and whatever. I only wanted to learn how to add numbers. Okay, I wanted to learn how to do addition, nothing else. What does it take for a baby transformer to learn how to add? And so this sounds like a trivial question, but it's not trivial at all. So we've spent years understanding why this is not a trivial question, me and a lot of other people outside of my group. And it turns out that addition and a lot of arithmetic operations are some of the cleanest, I will call it like mini laboratories for studying how language models and transformers learn compositional sort of multi-step algorithmic procedures. So it's a very clean sort of microcosm, if you will, to study these types of questions. And so I'm not going to tell you exactly what has happened. There's been a ton of work in understanding The sort of like, the quality of the data, how the intermediate steps and chain of thought helps quite a lot. There is scaling laws for addition, how bigger models help, how more data helps. There's a big question, which is basically that of length generalization, which is like, I train my model to do 10-digit addition, but will it know how to do 11-digit addition? The answer is no, by the way. Anyway, so the point is like, we've sort of like uncovered a lot of facets of this problem and try to answer a lot of those questions related to what does it take for a tiny transformer to learn how to add numbers. And the problem is that there is something that always bothered me. We always used to end up training more than 1 million parameter models. And this is just to add 5 and 6-digit numbers. So then I kept asking my students, I'm like, can you just explain to me, why are we training? I mean, this is still a tiny model in comparison to, like, I don't know, GPT and whatnot, right? So these are small models, but they're still very large for what they're doing. And I always had this bothering question, which is, why are we and everybody else training huge models for addition? And most of these papers that I'm citing here, they all have like, 1 or 10 million parameter models. They're small enough to train on a GPU or even locally, but they're still enormous, right? So this bothered me for a long time until this February. Okay, so this is sort of like, just introductory on project number 1. Which is basically, okay, now, I don't have to bother my students. They didn't have an exact answer to my question of like, why are we training a 1 million model? And I gave the question to Claude Code and Codex, which was basically, again, same format as I explained before. And then we kind of like, go into the details of like, what are the objectives that we want? And I want 3 things. First of all, make sure that the model can add 10-digit numbers with accuracy, let's say 99%. Minimize the parameter count. And I want to point here that this is objective number 2, right? So maybe a secondary objective. And at the end of the day, I would like a report to read exactly what happened. Okay, so this was basically the 3 objectives in a longer prompt that was given to both Claude Code and Codex, right? Again, the goal is train the smallest possible transformer that can add 10-digit numbers. Claude Code first, so it went about it very systematically. It was kind of like a textbook, really good student, sort of like, going through a bunch of interesting discoveries. So first of all, discover grokking. If you don't know what grokking is, it basically is when a model trains for a long time, the training error goes down, but the test error is crappy. It's like, you can't add, and then it just flips, and the model is able to add now 10-digit numbers. So it discovered grokking, that, these models and on this particular setting, they exhibit this sort of interesting phenomenon. And then it did an interesting thing. So it said, I'm going to find first a large transformer that can actually solve this. And then I will work down by doing some form of very simple architectural search. So I find a model that works. It has the specifications of a perfect, 10-digit adder. And then it kind of like, starts making it smaller and smaller. And so it scans through architectures, different depths, different widths, making head counts smaller and whatnot. And it identified what, Claude called sort of like a parameter phase transition, where below that, the model was not adding numbers sort of robustly anymore. And then it just sort of stopped scaling. So basically it said, here's a large transformer. I'm going to scale down, scale down, scale down, scale down. Oh, at some point, it doesn't work anymore. And then I'll just stop here. So that point was basically 6,000 parameters. So Claude Code managed to go from the 10 million whatever parameter model we were training for all these years, wasting GPU and NSF funds on training transformers to be calculators. And it found a very small one. And actually went back to my students and I'm like, so have you tried training like a 6,000 parameter transformer? And they're like, no, we actually haven't. And I'm like, it actually exists. So anyway, so they verified this, that it actually works. And I verified it actually works as well on a separate test set from the one that the agent was working. But the whole point, the bottom line of all this is that the agent now has done what I consider a mini research project. It basically autonomously did auto research. So this was, if you've seen Karpathy's auto research, this thing was like, I don't know, 2-3 weeks before that. And I basically figured out that the model can perform this automatic hyperparameter search, and what a student would basically do. It was kind of crazy. And it did everything, right? So it did like, full accuracy on 10-digit, small parameter count. We don't know if it's minimal yet. We'll see in a second. And then it wrote an amazing report at the end of the day. It's pretty awesome. A+, if you were to ask me. Now I went to Codex. I was like, let's see, it's two different agents. Probably they will do different things. So I went to Codex, OpenAI's agent, and it was the same prompt. And Codex basically found a large model that worked and sort of searched in that close vicinity of architectures and parameters and stayed there and basically stopped at some point. And I asked it, I literally pasted Claude's solution, Claude Code solution, and I asked it, why did you stop? Like, why did you just not? It seems like better models exist, smaller parameter transformers exist. Why did you actually stop? And it basically said that they optimized for making sure that we have a working solution effectively. And so what was, I think, really interesting to me is I was curious if the reason why this happened is because I asked for parameter count to be a secondary objective. Like I went back to my prompt and my prompt said objective, primary objective, find the transformer that works, secondary objective, make it as small as possible. And I think what happened is Codex took it very literally. So maybe listing parameter size as a secondary objective was interpreted that, it's an objective, but whatever, it doesn't matter if we really optimize for it. So then I went back to the prompt and I said exactly the same thing. I changed one thing, which was basically instead of saying secondary objective, I said it's not secondary, it's like equal with capital letters. It's an equal objective, make the parameters as small as possible. And Codex did something mind-blowing, I think. Again, I will call this my mini research because it basically found something I was not aware of. And I've been working in this area for quite a long time. So Codex did something really cool. So let's see what it did. So basically, it went around trying just training in a normal way, autoregressive, data generation in a normal way. And then at some point, it figured out you can apply a trick. So instead of encoding each individual number as a single token and as a single embedding, it basically invented a new tokenization that it sort of named as, how did it call it? I have it here somewhere. Per token, you call it per token. So what is a per token? So basically, let's say you want to add these 2-digit numbers, the ones I have in this rainbow colors. So what it did is basically paired together the digits from the two numbers that correspond to the same index. So the least significant 2 digits, it paired in one token. So this would be token 35. Instead of having two separate numbers, it was like token 35. And for 77, it was token 77, right? So basically now you have, instead of 10 tokens, so your original tokens would be 0, 1, 2, 3, 4, 5, blah, 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 9. Now you have 100 tokens, but there's something pretty genius about this. Once you do this tokenization, you don't need to learn addition anymore in the classic sense. All the model needs to learn is memorize a table of T35 is always 8. No matter where T35 is, it doesn't matter where it is, it's always 8, right? So basically, it in some weird way shortcuts the difficulty of learning addition. So the difficulty of learning addition transformers is basically figuring out how to apply the local addition rule on every single index, right? So then it sort of like relieved itself from one of the burdens of learning the addition algorithm, because effectively you need to now memorize part of the circuit, if you will. And this simplifies architecture significantly, right? So this was pretty crazy. I've never seen this trick anywhere in the literature. And what this allowed the model to do was basically train a model that now is only 1,000 parameters, so 6 times less than the Claude solution. Yes, there's a hand up. Sorry.
Go ahead.
Yeah, I mean, so T35 isn't always 8 if there's a carry, right?
T35 is T35 is always an 8, even if you have a carry. But T77.
Oh, sorry, yeah. T77 is. Yeah, or there's certain ones that are not always.
Correct. That's right. So like, for example, T54, it would depend on the previous thing. But I think the main point is effectively what happens here is like you don't need to learn addition. All you need to learn is memorize the result and an if. So the if would say your result is 8, or let's say you have T54. Your result is 9, and if the previous thing had a whatever a 1 for a carry, then it's a 10, right? So basically, it's lookup plus 1 effectively, which is simpler than doing addition on the individual tokens. That is, by the way, my interpretation for why I think it's an easier operation, but I can with confidence say that this is what unlocked the lower parameter count. Now, why it happens, this is just my interpretation, but it could be a different one.
Okay, thanks.
Cool. All right. So, long story short, it did something similar with Claude Code in terms of doing now an architecture sweep, and then it found something that was much tinier than before. It's like 1.6 thousand parameters. The cool thing also is that it did not push accuracy. So Claude Code went to 100% accuracy, but Codex stopped at 99%. It's pretty cool because I told it you only have to be above 99%. But I would say this is super cool. It's cool. For me, the biggest finding here is that the agents that we use are very sensitive to over or under specifying your objectives in ways that you wouldn't sort of realize until you kind of try them out. And each one of the, if you use Claude or Codex, they put you in really different research grooves as well. They find different solutions and they kind of they follow different paths, which I think was really cool. So anyway, bottom line is we went from a million parameter model that does addition to a 1,000 parameter model. I thought that was really cool. It partially answered my question that I had for a couple of years. But then I was still curious, is this the smallest transformer that can add? And so I was like, this is a good time to go back to the community. So I asked Claude Code to build me a leaderboard on GitHub. And we would have submissions coming as issues that whoever wants can post an issue on that GitHub repository, which I call Ladderboard. We review them, and by we I mean Claude reviews them on a hidden unit test, and we update the leaderboard. And within 5 days, we had more than 50 submissions, and the current best 10-digit transformer is a 6-parameter model. Okay, so we went from 10 million to 6 parameters. Okay. Now, if you're a little cynical, you'll be like, who cares? Why does this matter? I wanna walk you a little bit why this I think matters, at least to me. So a few cool things happened, and these were all powered by agents, right? So I sort of steered a little bit and had the idea, but whatever, this was enabled by agents. So first of all, I answered my year-long question. After 4 years of wondering, I now have a number. You can add 10-digit numbers with a 6-parameter transformer, and this is really cool because the number of parameters is smaller than the input length. Pretty awesome. Second, people actually engaged with it. The leaderboard turned out into its own little community. There were a lot of sort of, interesting insights in terms of what architectures work at that small scale and whatnot. And this was a lot of fun. And third one is that some smart kids from Stanford took basically took this sort of mini auto research question, and they turned it into a Harbor environment for reinforcement learning. So now, I don't know if you've ever played with Harbor. It's sort of it's a framework where you can effectively define environments in a sandbox with particular goals or unit tests, and then you can train your models on them. So Adderboard is now part of Harbor, of the Harbor framework. And then Terence Tao also, mentioned this sort of whole. So he had the Duarquez interview, and he talked about how it is a good idea to play with these small laboratories that give us insights into how these models work. So long story short, it was legitimately cool, and this took very little effort. And basically, the only thing that happened, I was like, I'll just do it, whatever. I don't need to know how to code to basically answer these questions. The technical burden from doing all the work now is completely lifted by the agents, and that was a magical moment. So that was vignette number 1. Okay. So what did
I believe
learn?
we have a question. Sorry, Dimitris, pardon me. Ruben, did you have a question?
Pausing here and yes, happy to take any questions.
Hi, yes, this is really cool. I was just wondering if there is any additional insight to go from 1600 parameters to 6. Any
Yes.
other cool trick like the one you found?
Yes, there are a lot of cool things. I will summarize them effectively into. Let me also kind of like, there's two types of solutions. One solution is I can hand code the parameters of the model. What does it mean? I won't train the model. I will actually go in and, hand code the weights. So they actually, the model does what I want. Or I can still push on training by doing synthetic data innovations, but also architectural innovations. Among both of those threads, the hard-coded transformers and the trained transformers, there were two emerging sort of, let's call them paradigms, if you will. So one was that there was a ton of parameter sharing. So what that means is that basically, maybe you have a bunch of heads, you tie them together. So like two heads are doing sort of like the same thing. Or you have sort of embeddings that are kind of like, that was the second one. So there were three. So embeddings that are low rank. And so again, there is parameter sharing, but like in the embedding space. And the third one was that basically for addition, because it's such a specific problem, you can kind of like in some ways pick positional encodings that are very tuned to the thing that you want to solve. And that tends to matter quite a lot. A lot of those things are not general purpose, like, the embeddings discovered are not super interesting in non-arithmetic contexts. But I think the parameter sharing across different heads and layers is very cool. And I mean, we've seen this also in practice being a good idea. So if you go in on the GitHub repository where the leaderboard is, the submissions next to them have sort of like, what's your model? Like what's kind of like the innovation sort of like in your model in comparison to the previous ones. And there's a cool convergence of methods. Like, in the beginning, people are trying a bunch of random stuff. And then, there's sort of like this convergence of like, there's these three ideas that really contribute into being able to minimize the scale of the transformer.
Blaine, we have a question in the room, Blaine, and then Pranav, I did see your hand up, so I'll come to you after the room question. Thank you. Go, Blaine.
Just an observation that you might be able to minimize things a bit further if you, maybe you've already done this, but the token like 4.5 and 5.4, you could make those the same token. You could just have the encoder. You could have the encoder just take the minimum one.
Yeah, that's a good observation. Honestly, yeah, I have to go back to the submissions. I do think that a lot of them didn't use pair tokens at the end of the day. They used like just character level tokenization, but I think you can do a lot of cool stuff with like, basically chunking tokens together and in some ways, like the more you overfit to the task you want to solve, there may be ways to do even better things. But I do think that there may be, so there's an interesting question, which is basically, is 6 parameter the minimum? Like there must be some, I don't know, complex the theoretical minimum where you can't go below, but I don't know if it's 6 or below, but I think we may be very close to the minimum.
Cool.
Thank you, Blaine. Pranav?
Yeah, so actually, in parallel, I was opening up your leaderboard. So the 6-parameter model, right? Like I could literally write out if I write out the math of a transformer, right? I could write out the equation. And does that, like, if I write out the equation, is it that a simple expression? Like, so that's my first question. Yeah, like, and does it map to any research literature?
So yeah, so I suppose, so you could write out the architecture of the transformer. I guess maybe, I don't know if I'm misreading your question, but one could say, well, I have an MLP layer. The MLP already does addition. Like, what does it mean to train the model to add numbers if it can add numbers already? So I think that the one specific thing is that there is the tokenization layer that kind of like quantizes. Like you kind of have to map from characters to positional embeddings, and then the positional embeddings are the ones that are pushed in the network, and you basically work on them. But I don't know if is this what you're asking? Sorry, I'm not sure I got your question.
Yeah, like so let's say after that first tokenization step. So now I know my equations like QK transpose softmax like over square root of dk times v, and then like after that there's an MLP layer, and for that 6-parameter transformer, like I could write down the equation, right? Like it should be not a very complex equation from what I guess. Like I guess the encoding part will be complex, which has all these.
Yeah, so I think honestly, here's what happens. The smaller the model is, the more weird the solutions work. In fact, in one of the submissions, it was not the smallest one. It was in the order of 30 parameters. the person that created the submission also created a very long blog post explaining how it works. That is just a data point as to like unpacking what the equations mean back to addition is actually a little tricky. So it's not basic. Like if I were to show you the 6-parameter model, it's not obviously how it works somehow. So by that, what I mean is that because you have parameter time, you have specific embeddings, you kind of have to figure out, does 12 plus 10 map to the same number? Like, is this actually running the algorithm? So maybe perhaps a way to think about this is like the transformer architecture defines some weird primitives. Think of this almost as assembly, right? How do you implement a 10-digit adder in assembly code? Now the assembly code is much nastier because it's like linear algebra. It's not like programmatic operations. So you have to kind of map programmatic operations and algorithmic primitives. I mean, it's a simple one. It's just addition. But like, force the model to do them in such a way that you minimize parameters. So it's a little bit too, I personally, when I see the architectures, I don't understand what they're doing. Like if you were to show me the and I've seen the 6-parameter thing, I have no idea why, like I can't explain to you why it works. I know it works from the unit test, but if you were to tell me, point to what parameter is doing what, I don't know.
Okay. And also like 6 parameters, somehow I can't wrap my head around it because
Pranav,
like
because we
yeah,
don't have
yeah.
much time left, is
Sure,
it possible to take it offline, the rest of it?
Yeah, sounds good. Yeah.
Okay,
Happy to
thank
chat
you.
back. Yeah. Good question, by the way. Yeah, these are really good questions. Okay, cool. All right, so summarize, the main idea, the main thing I want you to take from this is that you can actually now scratch cute and speculative ideas that normally you would ignore for years. And I think this is very empowering, at least for the way that I approach research. So that was a very cool sort of experiment number one for me. Encouraged by this, I tried something else. So the second vignette is about the idea that we don't have to run every evaluation because evaluations are very expensive. And in many cases, I don't know if, I'm sure a lot of you are following model releases. I think this is from Kimi K 2.5. Model releases usually come with 40 plus evaluations on different benchmarks. And the question I really had is whether we need all of them. And the reason why I'm asking this question is because this table of evaluations runs multiple times, as you probably already know, while you're training the model, while you're figuring out design choices, while you say across all these checkpoints that let's look at the evals, this is the one we're releasing. You're running this a lot, right? And this is a very high cost. Evaluations are really expensive, especially agentic evaluations. Terminal bench, my favorite benchmark right now, which is basically I give my model access to a computer and I ask it to solve tasks. Can it solve those tasks? Terminal bench is a very expensive benchmark, and it can be upwards to $1,000 to $10,000 to evaluate a single model just once. So it's a very expensive benchmark. And if there's somehow a magical way to avoid doing that while you're trying to design good models, it would be awesome, right? And so the question I had is basically, are most of these, so step number one, I'm like, okay, to even start asking the question of whether we can avoid evaluating models, can I collect all possible models and benchmarks we have right now? So I tasked Claude Code with finding from public repositories and release reports and blah, 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 all the benchmarks that it could find for all possible models that it could find. So it built a 90 model by 50 benchmark matrix. And every single release it could find was there. It was rough. It was a very incomplete matrix. Only 1/3 of it had entries, and the rest did not have entries. And again, this is sort of like a data scraping thing that a human would take, I don't know, maybe a week to do, but it was very easy with the agent. So this literally took less than an afternoon. So I collect this incomplete matrix, and I want to figure out if there is any redundancy to it. But before figuring this out, I'll give you a little test. So we have 3 models here of the previous generation. This is like a few months old. So Opus 4.6, GPT 5.2, and Gemini 3 Pro. And they're evaluated across 3 benchmarks, GPQ-A, which is sort of like a science STEM type of a benchmark, AIME, which is IMO level competition math, or pre-IMO, I should say, and SWE-bench, which is a programming benchmark. And I have a missing entry here for you with question marks. how much does GPT score on GPQA? And if you look a little bit at the columns and the rows, you will see that the numbers are kind of like similar in some way. The models seem to be scoring similarly with other models. And there is some correlation between perhaps the benchmarks as well. So if I were to guess, I would say that the question marks are probably between 91 to 94, just because of how close GPT-5 looks to Opus 4. And I would be right. It's the number is actually 93, right? So I didn't really, the point I want to make is that I did not need to evaluate GPT 5.2 on GPQA to know what the score was. I could kind of like smell what the score would be given everything else, right? And I didn't do any special trick, right? So this happens because anytime you have a table where the rows and the columns look very similar to each other, you can infer missing entries, right? So this is sort of like the idea I'm gonna be, this is basically what caused me to think about this question, that like, there seems to be a lot of similarity between models and their scores across evaluations. And so how many, if you look at the incomplete matrix of models and evaluations, you can ask basically how many different patterns are there in that matrix, right? So and the answer is basically 2. So the idea is that you can now approximate, you can take complete submatrices of the original incomplete matrix, and you can do SVD. You can just look at the top principal components, and you can ask how much or how many of those components do I need to approximate the matrix very well. And the rough answer is you only need 2 components to approximate very well that matrix evaluation, that model evaluation matrix, okay? So to make this a little bit more, so what do I mean by 2 numbers? So the whole idea and the first sort of mini scientific finding is that you can represent each model with 2 numbers and each benchmark with another 2 numbers. I'm going to put some interpretation in them. It's not necessarily accurate, but you can think of every model as having 2 scores. How good is it at general skills, and how good is it at hard reasoning tasks? And every benchmark effectively tests 2 qualities. How good is a model at general stuff, and how good is a model at reasoning stuff? So basically, is the benchmark a general knowledge or a reasoning benchmark, right? The score of a given model, M, on a benchmark B is just the inner product of these two-dimensional vectors, right? So for example, GPT-4, let's say it's represented by numbers 8 and 2, and AIME is also represented by numbers 1 and 8. When I take the inner product of these 2 numbers, I get a score of 24%, which would be close to the actual score of GPT-4 on AIME. Now, the whole point of this slide is that every model can actually indeed be embedded in 2 numbers, and every benchmark can also be embedded in 2 numbers. And that structure, which we would call a low-rank structure, is what will allow me in the next slide to predict whatever is missing. So the fact that this matrix has a low-rank structure will allow me to predict whatever scores have not been evaluated yet. And so BenchPress is basically a tool that, again, this was a prompt that I gave to Claude. I asked Claude to basically scan all possible prediction methods, from regression, matrix completion, nearest neighbor, whatever you want. So what's the goal of the prediction? I have a new model, GPT 5.5. I evaluated on AIME, MMLU Pro, and SWE-Bench, and I want to ask, given these scores and all of the past scores for all other models and all other benchmarks, predict the ARC AGI score for GPT 5.5. So that's the goal here. I want to predict a score without running the benchmark, okay? And basically, by doing, so how did Claude arrive at this solution? It did a lot of holdout testing. So holding out one model and the scores of one model, a bunch of predictive methods, again, matrix completion, regression, anything you learned in statistics 101 and 102 and whatever, and machine learning and everything. Try everything and their combination, okay? That took an afternoon. And then at the end of the day, Claude figured out that the best thing is just rank 2 matrix completion. I don't know if you've ever sort of studied matrix completion. I know Amin knows what matrix completion is, so offline he can explain. But the main idea is I have a matrix that I have some rankings in the matrix, this actually originates from the Netflix prize sort of thing, where basically people were trying to build predictive algorithms for Netflix to predict how much would I like a specific movie that I haven't seen, so that Netflix could actually recommend that movie to me. So this is exactly the same idea, but for models and benchmarks. Okay, so I want to predict benchmarks that have not been evaluated yet, right? So Claude tries all these methods, and it arrives at a finding, which is basically all you need to do is a rank 2 matrix completion, which means exactly what I told you before. Every model is represented by 2 numbers. Every benchmark is represented by 2 numbers, and I can infer the score of model I on benchmark J by taking the inner product of these 2-dimensional vectors, okay? So what this allows us now to do is we can now predict unrun benchmarks, okay? So this is roughly the method. Again, there's, if you didn't get exactly what's happening, the only thing you have to sort of understand is that there is some way, which is not very magical, there's a way to map a model, GPT-5, into 2 numbers. I don't know, 0.9 and 0.1. And the same magic sort of like technique to give you 2 numbers that characterizes well a benchmark. And from these identity numbers, if you will, or these sort of like ways of characterizing or embedding models and benchmarks, you can predict stuff you haven't seen yet. Okay, so this is roughly what the method does. If you don't quite get the details, it's fine, because I'm also rushing over it. But the whole point, the goal is to predict stuff. Can we predict now things that we haven't run? So here's an example. If you take one sort of sentence from this second vignette, is that bench press can basically predict 5 benchmark evaluations by only uncovering 5 of them within 5% error in 1 second with no GPUs, right? So basically you get a free tool to run benchmarks without running benchmarks. So let me give you like 2 examples. So let's look at DeepSeek V4 Pro, right? So the bottom figure. What this shows is accuracy of predicting terminal bench 2 that costs like, I don't know, $10,000 as a function of benchmarks that I reveal from DeepSeek V4. How do I reveal them? I go on the scoreboard. So when DeepSeek released this model, they gave us the scores. And by randomly revealing sort of these scores, I can get a better approximation of terminal bench. And within, I don't know, 5 benchmarks, I can have a plus minus 5% accuracy prediction on terminal bench for DeepSeek V4. And this is sort of like an average case prediction. Like in many cases, it's much better. Like with 2 or 3 randomly uncovered benchmarks, you can get like a, in 5-4 reasoning plus, we get a perfect prediction with 3 benchmarks. Okay, so this is actually pretty powerful, and it's cheap. It costs nothing. I know I don't have much time. I want to summarize the second vignette by saying, if you were to ask me what benchmarks should I run that are most predictive of models, we have a paper. I'm writing a paper on this now, which is basically saying, if you want 5 benchmarks that from them you can predict your performance on models, this is GPQA, Humanities Last Exam, Codeforces, MMLU Pro, and ArcAGI. With those 5 benchmarks, you can predict within less than 4% error everything else for your model. I think this is really cool. And this is really cool again because it's not cheap. I built this prediction on my laptop with 0 GPUs. Who can use this? People that don't have 10,000 GPUs to run evals because they have they can burn resources. So this is really good if you wanna try the ideas quickly, and if you don't have infinite GPUs. I know that I only have 5 minutes, and I want to budget my time correctly. Am I reading the time right? I mean, is it like 5 more minutes? What do you think?
Yeah, I think we can do 5 more
Yes.
minutes. I know, Supriti, you have a quick question before we move on to the last vignette.
Oh, this is super cool, Dimitris, and thank you so much for this talk. I had a question about bench press, actually. Like, did you run statistical significance over this? And I was wondering if, this is also under the assumption that the random benchmark would have something in common with the other general or reasoning benchmark, right? Like, there would be redundancies in the new benchmark. If not, I'm still a bit, I think, confused how like a random benchmark could be mapped to existing benchmarks.
Yes, basically just to quickly address both points. So the first point is, does this come with some way of knowing whether to trust the numbers or not? So the quick answer is yes. So in the paper, we actually will release a tool as well, where you plug in your model with some benchmarks and you get the predictions and you get a sort of a confidence interval that tells you how confident we are for the prediction. So there is a trust score, if you will. On the second question, there's no assumption of similarity. So this basically says, I have a black box. The black box does not see names, does not see benchmark styles, explanation of what things are, whatever. It just gives you a prediction. And that prediction will be either good or bad. It's going to be bad for benchmarks that are testing new skills. So we actually tested this out. There's a new benchmark called the bullshit bench. So bullshit bench is a very hard to predict benchmark, right? So this is not a guarantee that among all benchmarks we can predict everything. This says that on the median or the average benchmark, if you will, we're very good at predicting. So like I guess here, in this case, the choices that I selected some of, once I consider expensive, like HLE is an expensive benchmark and terminal bench is an expensive benchmark, right? So that's why I selected these particular ones. But there are benchmarks that will be harder, and we do have correlation of like, we have correlation studies of basically how much does benchmark A correlate with B and how predictive it is. And there are some that are not very predictive of other benchmarks, and there are some benchmarks also not predicted well by others.
I see. Also, I was wondering, I trust rate, but what would be a random?
With the time limits, would we be able to save that question for offline? The next part?
Yeah, for sure.
Thank you. I really appreciate it. Yeah. Dimitris, back over to you.
Yes. That was a great question. Again, I would love to chat offline as well. Okay, I'm gonna skip this. Again, bottom line. The bottom line of the second vignette is, I feel, again, with very little effort, I scratched the research seats, and now it has become, I'm working with some of my direct reports at Microsoft to make this into an actual full-blown tool. And this basically started from like a silly question, right? Again, this is really cool, and if you will, the lesson in terms of the science is that if you're building benchmarks, you can test how predictable your benchmark is. And if it's very predictable, maybe it's measuring something that is already measured very well by other benchmarks. Anyway, so I know that we're very tight on time, and I will gloss over the last vignette, which maybe is my favorite and also the most useless. So it's okay if I skip most of it. But I had this silly question for a long time, and I'll try to explain how this question was born in my head. But for a long time, in my group, we're trying to understand how transformers work. Okay, so what do I mean by how transformers work? Basically, we want to understand the computational power of transformers, and we had this paper called, if you heard about looped transformers, we came up with a name. Okay, so we were working on loop transformers, trying to understand if they can mimic a computer. So what does it mean to mimic a computer? A computer basically has memory. It can read and write from memory. It has conditional branching, and it loops until it halts. Right? So that's, I would say, a computer is a lot more things than that, but a computer at least needs these things. It needs memory, conditional branching, and effectively looping. And we try to figure out to what extent a transformer can actually implement a full-blown computer, not like a Turing machine on the theoretical sphere, something that I can actually write programs in assembly on. And so we found a very simple language called sublec, which is an assembly language of one instruction. There literally exists an operating system for sublec where you can play Doom. It's only one command, which is basically reading two memory cells, subtracting them. If negative, the program counter jumps to a specific register. If positive, program counter ++. So this is sort of like, there's a lot more substrate to it, but the whole point is like this single command can define a Turing complete language on which you can build a fully functional operating system, which is really cool. So then at some point in 2022, I asked my student, can we build a computer with a transformer? Imagine the pain. I guess imagine the pain of the student. And the students, there were a couple of incredible students working on that. That they basically showed that you can actually, in fact, build a transformer. What does it mean, build a transformer? Handpick the weights so it runs programs in this really peculiar language. Okay, so we managed to do this, and there are some implications. I won't go into that. I won't even go into like why did we care about this, but there was this question that I had for a long time. Can we train a computer? Can we train a transformer to basically compile programs, right? So I give the transformer a program, and can it run Fibonacci? Can it run, can I write, I don't know, whatever. Can I play Doom on a transformer that has been trained from scratch, all right? What is the significance of this question? Of like, why would you want to train a computer? It's because this would be the first computer ever found by gradient descent. It would be a computer that is built by non-computer parts. I'm putting an asterisk there, can explain what I mean. And it would effectively be Turing completeness emerging from non-Turing completeness. So it's, I don't know, this is cool, right? So this checks all the boxes of coolness to me. And I want to figure out if we can train a computer. We had this question for a couple of years. My students were not able to figure out whether this is possible. There were some training issues. I won't go into the details of what happened, but the answer is yes. We can now train a computer. Claude Code did that for me a couple months ago. I'll skip what happened. What happened is very cool, but unfortunately, there's no time to go into it. But the main point here, first of all, I think there is some historical significance, because this is in fact indeed the first trained computer that was found by a non-intelligent method. But also, again, this sort of pattern matches, again, the style of problems that I had for a long time, which is basically, it's hard to justify the time of a human to work on this. I still think it's an interesting question, but it's a question that I was only able to answer once someone was able to do the technical work for free for me, okay? So I'm gonna skip that, and I just wanna conclude with a little bit of what does this all mean for all of us? Because I think there are some implications. Oh yeah, by the way, every single one of these projects took a day. Okay, so that's another crazy part. They sound like, I don't know, maybe more than a day. Beginning to end, it was a day and a half. It took me more time to write about them on my blog rather than actually running them. Anyway, so I think agents allow us to do a new kind of research that I call high temperature research. You can do a lot more. You can ask odd, weird questions that cross different domains that you're not comfortable with, and you can still dive really deep. So it's not like, breath on just on the surface. You can actually dive deeper. But the problem is that you also have much higher variance, because now you are tasked to be a very strong verifier. And there is a lot of cases where it was really easy for me to believe the result of the agent and to fool myself that what I see is the answer to the question, when in many cases it was not. So there's a lot more variance now, and we are tasked to be much stronger verifiers than we used to be before agents. But nevertheless, I think this really unlocks a new kind of research that for me has been, very rejuvenating. I feel it's a coming of age. 2026 is a coming of age year for me. But it's been very exciting, but also a little scary, because there's been many cases where it's really easy to fool yourself at what Claude Code is giving you back is the right thing, when in many cases it's not. So I do think we are in the golden age. I'm going to close in 2 slides, and sorry for keeping you an extra couple of minutes, but I do think that we are living through the golden age of asking questions. We have something close to a magic box. You throw in a question, and the first answer, the signal to whether what you're thinking about is reasonable or not, comes back to you for free, all right? There's no human effort that was spent in answering that question. And it's like having a tireless junior collaborator. And that's both amazing and terrifying. And so I sort of want to end with a question basically here. And it's a question that I genuinely don't have a good answer to. And I don't think anybody has a good answer to this question. And it's a very important question that we have to think about deeply. Because if we get the answer wrong, we'll wake up in 5 years with a generation of researchers that are great at prompts but bad at taste. And that's probably a worse world to be in. And I think if we get it right, I'm not sure exactly what right looks like, but I think, maybe we'll be able to use agents as our technical and intellectual extension. And there's still sort of technical grind that's happening, but it's happening at a much higher level than before. And I think the question is basically, if most of the technical burden is now lifted, like when I train students, I give them these things that I find them difficult to do now. I've completely lost the muscle of coding, but for them through coding, they would build taste, and they would also build the ability to verify if what they see is BS or non-BS, right? How do you teach that when the whole process of technical, arriving at the solution evaporates, right? So I don't have a good answer to that, but I think it's an important question. And I think we have to be deliberate about how we answer that, which raises one more question. What should we do now? And I don't think I have a recipe, but I guess I have one more thing I want to leave you with, which is basically that, we're again in the golden age of asking questions. And I hope we ask the right ones. And so thank you so much. And I'm really sorry I took 4 more minutes than my allocated time, but it was really great. And I really enjoyed the questions that you asked me.
Yeah, thank you very much.